Welcome to Real Physics. Today I have a guest, Jonathan Fay from Bristol University, and he is a, how should I say, a physicist and really interesting researcher. I should say that I'm really proud to have you here because I recently discovered that one of my first emails I got you get the notification from YouTube when you have new subscribers, and I discovered that you were one of the early subscribers in, I think, in 2016, and at a time where my channel had something like 180 subscribers. And yeah, it's really exciting to see that because you have done, in my view, incredible work, and I have to give you credit for that. It's really interesting. You're digging in the history of physics, and not just digging in the history, but really you're after something, yeah, very big. Because, well, we will talk about that, but the unification of inertia and gravity is such a huge problem. I mean, most of contemporary physicists wouldn't realize that, but I think, yeah, it's really something spectacular, and you found that, and you also reignited my own interest because, I mean, I had read the paper by Sciama, but as we have mentioned in this video, I'm sometimes I'm a lazy person, or I don't understand the full content. So you pointed my attention to this video, and with all this research, you're doing something very profound, something very important, and yeah, you're not only dealt with Dennis Sciama. Also, recently you have written a paper about Hans Reissner, which was completely unknown to me, I admit. So I really admire that approach, that you're so yeah, on the one side very diligently working in the history and finding all these papers, but also you're, I mean, that's not only that. You have to have a very deep intuition as a physicist, what is relevant and what is profound. And yeah, I think without being flattering too much, I think you're one of the most interesting scientists of current times. And I really appreciate this. I really appreciate to have you on my channel here. Hope the audience will enjoy this. And well, just tell me about your recent work, or your work in general, and well, maybe we can go to the technicalities also a little bit later, but let's start with the more accessible stuff. Let's say, how did you, I mean, yeah, or if you want, just tell the story historically, how you got interested, what's your motivation, yeah, what's the purpose behind, and then look also into more detail. Welcome here.
Thank you very much, Alexander. And yeah, and thank you for inviting me for this interview. I should correct you slightly that I'm not technically a physicist, because I'm training in the philosophy of physics.
Yeah, but you, I mean, you are a physicist and you have studied it. I don't. Yeah, man, I'm not interested in this. So you're always, I should have said you're always a very modest person. That's also, I think, something to mention here, because despite the very profound impact the things you're dealing with they have, you give credit to the people who have worked on this, and you mention a lot of other people's contributions. So this is, I think it's also a sign of a good scientist. But well, okay, I know that you are working in the philosophy of science department, but I mean, there is no question that you are a full-fledged physicist. Let's say, okay, that he knows what he's doing. I mean, we had these discussions in Bonn last year, so yeah, there are limits to modesty. Jonathan.
Okay, well, thank you. Well, I say that because I mean, part of why I'm doing a philosophy of physics PhD is because I wanted to have the freedom to do this kind of research. And I was skeptical that I'd be able to find that within the physics department. Uh, so, so I mean, do you want me to tell the audience a little bit about how my background or how I got interested in these ideas? I mean, you already mentioned that back in 2016, I think you said, I would have subscribed to your channel. So I must have been about 19 years old at the time.
It's very young. Yeah, that's incredible. Yeah. Yeah.
So
Yeah. I
I
mean,
would have been studying.
I mean, the audience, I mean, they can read your papers, but, and that's one thing. And we should also be honest, if you really want to dive into this matter, thinking about gravity and inertia, I mean, you have to do very hard, also technical work in reading papers, but that's not the primary purpose of this conversation. It should provide also a motivation in your personal way, and maybe motivate some other guy who to enter this field. So it's nice if you tell the story, you're interested in physics maybe.
Right. Well, yeah. So I think I was always interested in the sort of fundamental questions. I remember before I studied university, well, when I got interested in physics, I started looking at a lot of, these paradoxes in quantum mechanics to try to figure out what was going on there and this kind of thing. And then I must have come across your work as well, talking about Mach's principle. And back then that sort of sparked my interest. Um, and then I remember after getting a degree in physics, an integrated master's, I came back to these ideas about Mach's principle, and suddenly things were becoming a bit clearer to me, and I decided to switch over to do a master's in philosophy of physics. And and I started that master's already with the intention of pursuing this particular thesis um, concerning Mach's principle. I wanted to, on one hand, explore like the philosophical foundations of this idea, and on the other hand, look at the physical consequences of the principle. And in particular, I took it into the direction of what I've called, well, Mach's hypothesis and then Reissner's hypothesis and so on. So I've been distinguishing these terms. So yeah, and then after my master's, I went on to do the PhD program, also at Bristol, with the same supervisors who have been really great in giving me this freedom to do this research. And I started, doing more academic style, sort of historical research into these texts and finding things that I didn't expect. And so I've written some papers. I wrote a paper on the foundations of geometry. I wound up getting quite interested in Kant for some time.
By the way, I noticed also you have an incredible knowledge of philosophy. I'm ashamed sometimes how much you know with your young age, but all sorts of also physics related interesting philosophers. Yeah.
I have a very particular knowledge of philosophy, so I don't have the breadth of like a lot of philosophers, academic philosophers, but I have in the particular things I'm very interested in.
The good ones.
In my opinion.
Yeah.
Yeah. So, what do you want me to tell the audience a little bit more about the particular?
I mean, that to me that shows you have a very good intuition to go to the relevant stuff of fundamental physics, because it's not that easy, because there's such an information overflow if you're studying university papers. All the daily science business it's hard to find the relevant stuff, I think. And evidently you have had a very good intuition, and you must have got that feeling also, oh, this is really interesting, I mean, how should I explain? If you study physics, if you're a student, you start. I mean, there are lots of bright people, smart guys, doing very skilled in math and so on, and you're kind of, oh, I am the student who has to learn, and it's already difficult, and maybe I understand fully what all these gifted scientists and all these smart professors know, and you're almost not supposed to discover something new or something relevant, or you're just busy with just learning that incredible physics stuff. That's the message, which is I would say subconsciously transmitted to you as a student. But at a certain point, I mean, you also discovered, wow, this is huge. Say Sciama's thesis. This guy has resolved a problem Einstein wasn't fully aware of. I mean, we can say that, right? So, also a part of my question would be, how did you get that feeling this is really relevant? And well, to the audience also, how do we get the message across that there is something to be discovered, that there are problems in general relativity which are not settled, because I mean, people would just the usual mainstream physicist, the usual what you read in the journals is, oh, general relativity is so wonderful. I mean, just eat this and don't think about, But how do we communicate that the ideas of Marx have not been realized, and there is something to fix and something to discover and something, also even to revolutionize, I think, in gravitational physics. What's your take on that?
Well, I mean, I would say there's a lot of subtleties here. So, I mean, concerning, well, I want to push back a little bit about saying, that like pointing to very particular figures like Mach or Dennis Sciama. I mean, I've done this as well, but the more you read like the history, the more you find that a lot of these ideas sort of come and go, and they get sort of semi-developed, or even, for example, when we talk about Mach's principle, it's not completely clear that Mach was always committed to this. He sort of threw this out at one point and then maybe retracted it a bit at some other point. And so I think over the course of the history of physics, there are these little insights that sort of come and go. And by looking at the historical record, we can sort of try to see what keeps coming back and see what is it that seems to make the most sense with a bit of view of hindsight, and then reconstruct. And that's what I'm trying to do, is like reconstruct then a historical narrative, bringing together what I think are the most essential bits and pieces. And for that, I would say I've been guided by this kind of intuition about things. And I think that intuition, what it really comes down to is a desire not simply to have a physical theory that describes nature, but that sort of makes sense of it somehow, right? That sort of explains things. And I think this happens in science over the course of these unification moments in fundamental physics. So, for example, I mean, when Newton unifies celestial mechanics with earthly gravitation, right?
Exactly.
It is a big leap, in comparison to what they had before, even though a lot of the technical insights were kind of discovered by Kepler and people before that. By saying, that the bodies are pulled gravitationally and it's the same force that's causing things to fall on Earth.
That's the big idea, yeah.
Exactly. And once a unification like that happens, it's like irreversible. And there's a lot of controversies in the philosophy of science about, what is it that we've actually found out in these scientific theories, because it seems like the things that we were saying in one epoch were real completely change, and then as the science progresses, and it seems like we replace one type of thing with another, and so we don't know, was the ether real? Is it just fields? Is it space time? All of these concepts change and so on. But I think there are these unifications which reveal something deeper about nature, that regardless of the words that we name things with, will stay true, right? So it's true that the thing that, the reason why objects fall on Earth is the same reason why planets stay circulating around the sun, right?
Mm-hmm. Yeah.
And so that's kind of what I look out for, is like
Yeah.
hints of potential further unifications. That's what really gets me excited. And that's what's been guiding me towards, that's what got me interested in Mach's principle. Yeah.
That's also what I find fascinating in history, and why you have to do history, because you see the patterns. And as you said, Newton's example, what Newton did was explaining all the local gravities, say on all planets, with one huge unifying formula. There is big G, okay, and the mass, instead of all these little g's, which are explained away. So you have this kind of unification, and in the same way as Newton explained the little g's by the big G should be explained by Mach's principle, and relating that to all the other masses in the universe. And this is, for me, it's kind of obvious that you as a physicist, you have to explain the value of the gravitational constant. It's in a way, it's to me, it's as clear as daylight that there is something missing in because our current theories do not do that, right? We treat the gravitational constant as a god of modernity. We believe it's 6.67, and here God wrote this number down with his pencil, and but it's not. I don't know. How do you? Maybe I'm living in a bubble, but what is your take on that? Do you think by studying history you get a better picture of what is relevant, of what are the real revolutions in science, so we can possibly spot the next issues to solve?
I think so. I think you definitely. I mean, if I compare like those of my colleagues who are more concerned with history with those who are more concerned, oftentimes, in the philosophy of physics, with the technical details of current theories. People, if you're just concerning yourself with the technical details of current theories, you're going to get very good at that, but you're going to maybe lose a bit of historical perspective, and a bit of perspective on how theories can actually change, and how concepts shift around, and so on. And so I do think, I don't want to be too critical of my colleagues, but I do think that there's an advantage to having a more history-based approach. And also, it's made me humble, because I realized so many of the things I've thought.
Yeah. That's why I appreciate so much also what are you doing, because you find these interesting gems, because there are lots of papers even in history, and you easily get bored if you just randomly open some physics journal of 100 years ago, even if it's more interesting than today's journals. But still, it takes intuition, and it takes really something to spot these interesting things. And and I also agree that intuition versus doing calculations is what led to the big advances in theoretical physics. I see also Einstein's method in this context. He always admitted he was technically even weak compared to a Hilbert, compared to Henri Cartan, and even Hermann Weyl, dealing with differential geometry. But he had a very good intuition what could be physically relevant and what not. Yeah, and yeah, I think we are. It's humbling to see all these people. Not only Einstein. I mean, Einstein is the most famous and iconic figure in physics, but there are so many people who really had interesting thoughts, and that's yeah. I also I see this as a humble approach. Yeah, and that's the correct one. And in contrast, I mean, you have all these, not to be too critical of contemporary physicists, but let's say they tend to fall victim to this how to say, illusion of the focus of the present. Yeah, just dealing with what is in your mind. What you see is all what is your mind. Yeah, like Daniel Kahneman says. So it's really good to have that broad perspective. Yeah, yeah. There is one thing. I mean, how do you deal? I mean, I think for you and me, it's clear that we respect all these physicists, but there is one thing sometimes you have to deal with, I would call it the inner critic, and sometimes it's like, who are you, Alexander, or who are you, Jonathan, that do you think you can resolve something Einstein wasn't able to find out? Okay, who you believe to be, and how do you deal with that? How is it? It is sometimes scaring to be, if you see, and I'm convinced you see that. Okay, there is a problem which is unsolved, and which most of current physicists don't realize. Does that scare you, or how do you deal with that?
Well, again, like I try to read history, and construct a narrative to explain why, or like dig out a narrative rather to explain why things happened the way they did. So, for example, with, despite Einstein's intentions, Mach's principle doesn't really get fulfilled in general relativity. And part of this, I think you were just referring earlier to how Einstein was very intuitive, but less technically capable than some of his colleagues, which is definitely true. And this meant, for example, that although he wanted to implement Mach's principle through the general covariance principle, he wasn't able to really realize why this didn't work, because he wasn't good enough at the mathematics to really see what was going on. And um, once you dig into the subtleties and you don't idolize these figures too much, and you have to acknowledge, that a whole bunch of them are much smarter than you and so on. But you can see that they also make mistakes. So even Poincaré, who I really kind of idolized for a while when I was doing my master's, I came to see that he had actually made what I regard as a kind of silly mistake in one of his papers, and then I've mentioned it in my article on the relativity of magnitudes. And so, yeah, you come to see that, it's possible to situate yourself among these people in the past, and with, a bit of benefit of hindsight, see where they were right and where they were wrong, and then try to fix things from there. So,
yeah. That's also why I enjoy reading old papers, enjoy reading biographies, and because I mean, you almost, it's as if you would talk to these people and their mindset, and I think it's sometimes it's a healthier approach to science and a healthier approach to these fundamental problems we see back then 100 years ago than than we have today. Okay. Well, I mean, this is not to be to give a critique of the current scientific method. So maybe yeah, what we could pass on and maybe to be a little bit more technical or what is on the focus of your interest now concretely, how to unify inertia and gravity. We have Sciama's approach. By the way, the audience should watch maybe the talk you gave in Bonn last year, or my video about the Sciama, and you should certainly know something about the audience about Mach's principle, in the sense that the question is, I'm just repeating things now, but the question is, does it make a difference if we rotate here and the universe out there stands still, or we are standing still and the universe rotates? That's the key question. And Mach's answer is it doesn't make a difference. So every law of nature should be phrased in a way that it makes no difference between these two situations. But the actual gravitational theory does make a difference. So Mach's principle is not realized. And Sciama did realize that concrete problem, as you pointed out in your very, very good paper. And well, this is what you did with Sciama, and then you pointed also our attention to Hans Reissner, who is kind of a precursor to Sciama, in a way not as clear maybe, but on the other hand, it could be even more fundamental, as I understand, because it's also very attractive how he does things, very, very simple in a way. So what's your current interest? What's your currently, you think, the most promising thing you can work on?
Right. So maybe I can give a bit of background to how I got to this here, and this will link to some of the videos you've made previously on the channel.
Yeah, I can display the videos. Will do that, and we can also display some of the formulas, but certainly not the entire paper.
Yes. So I was initially, I remember reading Dennis Sciama's paper from 1953, which is essentially a chapter from his PhD thesis that he then publishes as a very short paper. And it's, if you look at the details mathematically, it's not a complete theory. It doesn't work completely. But what Sciama wants to emphasize is that it kind of captures the physical idea really well. And I think Sciama is sort of like aligned with you and I in this sense that he emphasizes the importance of like understanding things in a physical way, not just throwing some maths at it and closing your eyes or something. And so he deliberately makes, a simple theory that's incomplete in order to simply illustrate the concept. And
well, deliberately simple. I mean, it's not that he could have done it easily in a complete way. I mean, he started from the simple, but
exactly. Yeah.
It was. I mean, let's say it was just too difficult to complete it technically in a way that is aligned with also with special relativity, of course. Yeah.
Well, yeah, but in his view, which I think, I'm not sure if his argument is correct about this, but in his view, the correct theory had to be tensorial. So you had to have a rank 2 tensor potential rather than a vector potential. But he simply constructs a vector potential theory for the purposes of this illustrative model. And I remember reading this and reading it slightly differently than Sciama, because Sciama describes it as an explanation of inertia from gravitation. And this is something very similar to other models that were made, but using a Lagrangian formalism. Sciama instead uses an analogy with Maxwell's electromagnetism. where you modify the gravitational potential so that it has this vector part. And so you no longer just have this scalar gravitational potential, you also have this vector potential, so that when masses move, there's also a mass-mass interaction. And then you make this mass-mass interaction responsible for establishing inertial frames, and therefore also leading to the invariance of the universe under rotation. So if the whole universe rotates, it will rotate the inertial frame so that the physics stays the same. Right.
So all masses kind of create a field that drags
Yeah,
along,
exactly.
and yeah, it's similar to the static case would be the gravitational potential, just the sum over all masses divided by the distance, and that's the usual gravitational potential. And Sciama adds the idea of adding velocity and creating this extra field, and comes up with this wonderful derivation. I mean, the result is wonderful. I sometimes, well, the problem I might have is, why should we implement this analogy to electrodynamics in the first place? Yeah,
exactly. So I'll just note here that before Sciama's work, Schrödinger had also done the same thing, and then after Schrödinger, independently of Sciama, André Assis, who you've talked to, rediscovers Schrödinger's theory, basically exactly the same theory, and then my recent collaborator Dennis Brown, who you know as well, is very keen on Hans-Jürgen Trader's theory, which is also very similar.
Very interesting guy, this Hans-Jürgen Trader. Yeah.
And so this analogy with electromagnetism has been done several times, and Sciama's theory for me is just the most conceptually accessible, because it's written in a way that's like visually what you can. It's easier to understand what he's trying to do, and to understand the physical idea there. This was suggested.
Let me say that you did it already still better than Sciama, explaining things in a physics way.
Thanks. But this was suggested all the way back in 1896, I think, by the Friedlander brothers. So that's the first suggestion of this kind of way of implementing the relativity of inertia is in 1896 in a footnote from a booklet called On Absolute and Relative Motion, although in German. So that's an interesting little aside. But anyway, Sciama's theory and all of these electromagnetic analogies in general were described as ways of explaining inertia from a kind of like expanded vector gravitation. And I sort of intuitively saw it the other way around. And so I've been trying to interpret things in the opposite direction. But the reason it was done this way was that physicists, I think, especially in the 20th century, or especially in the second half of the 20th century, there's a view that gravity is less controversial than inertia. Inertia is the thing that's absolute, that refers to these absolutes that needs to be explained in a dynamical way, but there isn't like a desire to explain why gravity exists, right? Whereas I kind of see it the other way around, because from a philosophical perspective.
Let me emphasize this, because it's so important. I mean, still in current theories, these things are separated. Okay, you have inertia and you have gravity, and it's so mind-blowing that you have this formalism where, I mean, it comes out from the same formula, from the same term. You just take different derivatives. You have a spatial derivative, and you have a time derivative, and here is the centripetal force, and here is Newton's law of gravity. It's really something beautiful. Yeah. And if you haven't done so, the audience, look up this piece I will display in the video. Yeah, go ahead.
So where was I at? Oh, yeah. So I was saying, so to me, from a kind of philosophical perspective, it's the law of inertia is something that needs to exist necessarily. Like And I don't mean the law of inertia in the absolute sense of Newton, but I mean you need to have some kind of law of like where things are going to go when they're not subject to any other forces, like like electromagnetic forces or something. You need some motion that bodies resort to. It has to be defined somehow, right? Whatever that way may be. But then the existence of gravitation is kind of something that needs to be explained. There's no a priori reason why we should have gravitational attraction between bodies. And similarly, there's no a priori reason why the law of inertia should be fixed in a particular set of reference frames. So we need to explain on one hand the set of reference frames, and on the other hand, we need to explain why gravity exists. And so this is kind of how I see it conceptually. And in my view, a theory of the type of Sciama's is an attempt to explain both of those at the same time, right? You give a dynamical account of inertia, which means that masses are what establish the inertial frame. So you've explained why there's a preferred set of reference frames in your local physical system. But at the same time, from this dynamical account of inertia, you get this gravitational attraction. And I sort of there was always a little issue with this reading of Sciama's model, which I made I think a couple years ago now, which is that there isn't a complete justification for why the gravitational, the scalar part of the gravitational potential needs to be there. There's a kind of partial heuristic justification. I talk about this in my latest paper with Dennis
I
Brown.
see.
But it's not completely explained. And it's definitely, it's sort of partially explained, I think, I would argue, in Sciama's theory, and maybe, but it's not explained in theories like those of Schrödinger or Assis. So there's still the potential, I think, for like a deeper understanding. So even if this kind of theory of the type of Sciama's is correct, and it's a bunch of results that are associated may well be correct. I mean, there's possible links with the critical density condition in cosmology, which is very exciting. That's another unexplained fact of nature. The density of the cosmos is so close to the critical density.
Yeah, or in other words, I would phrase it that the gravitational constant is, we have the coincidence, it's c squared times the radius of the universe divided by the mass of the universe. That's the same thing, right? So, and this is if you talk about coincidences, I mean, coincidences have always been the hallmark of good inspirational theories and revolutions in science. I mean, Johann Jakob Balmer was inspired by coincidences. Kirchhoff and Weber were inspired by the c squared equals 1 over epsilon naught mu naught, which revolutionized the world, right? So you have to, you just have to have a closer look on these coincidences. It's not.
Yes, I would make a sort of point here that people I think look over is that there's a difference between a coincidence of like you bumped into your neighbor or something, some coincidence that happens in daily life, and that if you're schizophrenic, maybe you're going to be inclined to link the dots all the time. There's a difference between that and coincidences that have to do with the fundamental laws of physics, which is like a fact that's true forever, right? So if you have some coincidence to do with the constants of nature, this I think is something that needs explanation much more than some contingent matter of fact that you come across.
Yes, because if you coincidentally meet your neighbor in your holiday, it's not something that solves the questions that has to be explained. But in physics, you have also, you have to have explained this explanatory power of theories. There is a need to tell why it is this number and not another number. And
Yeah.
if you follow up all the revolutions basically have resolved, have eliminated that kind of arbitrary assumption and explained it. I mean, people would almost never phrase it the way I do it, but I think quantum mechanics, of course, it's an incredible building of theory, but at the very end, it boils down to explaining Rydberg's constant, found by Balmer, by other constants of nature. That's the incredible reduction here. Yeah. And so I mean, good physics, if we do physics, we have to strive for that kind of simplification. Yeah.
So I would totally agree with you. Like in all of these unifications, which is what I said earlier, is what I view as like the the true progress we make with fundamental theories in physics. All of these unifications come with a reduction in the number of natural constants, right? So yeah, I'm very much in agreement. So where was I concerned?
Yeah, I mean, you're Sciama. I mean, we were thinking about. I mean, we were at our conference last year. We all were racking our brains how to generalize, how to fix, how to. I mean, Sciama is not complete. I mean, we see a beautiful picture here, and we see the puzzles that the pieces connect very nicely, but there are huge gaps. On the other hand, we're not able to fill. Okay, and Jan was thinking about finding a metric, and how could that vector potential be the special case of a deeper underlying metric? Maybe this is promising, or maybe we don't need that. And I have always tried to emphasize the link to variable speed of light, because there are so many connections, even if Sciama doesn't mention that one. So yeah, this is one thing you're thinking about Sciama, and then you also had Reissner, of course.
Yeah, so I mean, maybe I should also link this a bit to the paper I wrote about Mach's principle, where essentially, I mean, I made the effort that this is something that's not really been done at all in the history of Mach's principle. People sort of say Mach's principle, but sometimes they mean different things, right? So I went to the effort of trying to distinguish the part that's a principle from the parts that's like a hypothesis about nature. And the principal part is just like relationalism, right? It's like the idea that what actually exists is the relations between things. That if you have a concept of space, of a passive kind of concept of space, then your motion through that space isn't something real. You only move with respect to other things, right? And so this is what I called Mach's principle. And then on the other hand, if you accept this idea, you kind of have to get rid of the way that Newton was thinking about inertia, because Newton attributed the preferred set of inertial reference frames to absolute space itself. But if you're a relationalist, you can't give that role to absolute space. You'd have to give it to some physically real thing.
Doesn't make sense, that kind of absolute space. Yeah, we should give credit also to Bishop Berkeley at this point, right? He was
yeah. He made similar critiques, and so you have to give this role for establishing the inertial frames to something that's physically real. And then Mach proposed two possible hypotheses, essentially. In his works, he proposes either there's some kind of field which determines the inertial frame, or what we call space. So this field is not itself physically real. It's just an abbreviated reference to the rest of the masses in the universe, right? And so this is where this idea comes from, that the masses somehow condition the inertial frame. And the real appeal of this idea only becomes clear once you link this with Einstein's equivalence principle. And this is to Einstein's credit that he really emphasized the equivalence principle. So Einstein noticed that the fact that all bodies accelerate the same, are subject to the same acceleration in free fall, tells us that the gravity, doesn't distinguish between any different materials. This is a property that gravity shares with inertial forces. So with the fictitious forces, when you're in an accelerated frame, all bodies will appear to accelerate the other way. The same with the same acceleration.
Then also concretely the bending of a light ray, right? So he compared this situation to free accelerated frame
Yes, it
and
was able to
gravitational field. In
argue.
both cases, you have the curvature of the light. Yeah.
Yeah. And so when you look at the equivalence principle in combination, which tells us that there's something in common between gravity and inertia, when you look at that in combination with Mach's principle, or Mach's hypothesis, sorry, what I called Mach's hypothesis, which suggests that inertia ought to have its origin in some interaction between masses, then these two fit very well together. But in combination, they kind of suggest that, well, what if by relativizing inertia, by making inertia, by making the inertial frames be defined by the rest of the masses in the universe, we get some kind of deviation from Newtonian inertia in our theory. And so this was what I've, in very vague terms, called Reissner's hypothesis. And the reason I called it that was because there's this paper in 1915 by Hans Reissner, where I think is the first sort of clear articulation of this idea that by relativizing inertia, somehow you're going to get gravity out as a side effect.
Yeah.
And I initially interpreted Dennis Sciama's theory in this way, but as I've said, there are some issues with this, because you could argue that you only need a vector potential theory, or maybe, I mean, there's arguments to be made that you don't need, that it doesn't it doesn't perfectly define a particular gravitational theory, right?
I see. So Reissner's approach is kind of cleaner in that sense that he just needs a Lagrangian. Right? This very simple. We can display that formula 6. It's very, very simple. The Lagrangian, just the sum over mi mj, two masses we talk about, and then divided by the everything is relative here. And interestingly, it depends only on the r dot squared on the distance, on the relative distance of these masses. That's very, very simple. Yeah. And of course, perfectly relational, right?
And what's quite interesting is, so Reissner wrote these two papers in 1914 and 1915, and exactly 60 years later, Julian Barbour writes a pair of papers, so in 1974 and 1975, which essentially perfectly correspond to the two papers of Reissner in the sense that he does the same thing in the first paper and then introduces the same innovation from the first one in the second paper. And so this is one of these coincidences when I was looking at the history of these theories that really kind of sticks out, and you think, well, if people keep coming up with the same thing, maybe there's something interesting here.
Yeah.
So what I was doing in this paper, that's in collaboration with Dennis Brown, of course, what we were doing here was going through the different theories that were proposed over the course of the 20th century and trying to distinguish, get into the details a little bit and look at their different features. And initially I came at this sort of very skeptical of Reissner's particular approach in his second paper, the way which is the one I've named Reissner's hypothesis after. And in the second paper, what he does is he proposes that inertial forces are caused by the relative motion of bodies with respect to one another, but those bodies are composed of particles that are jiggling around and vibrating and moving at high speeds, right? In irregular ways. And he suggests that this motion is causing an additional interaction with other bodies, which then manifests as a gravitational force, right?
Very, very, very interesting. And again, compliments to your work, because I mean it's kind of embarrassing for me, because I mean Reissner wrote in German, and I myself I admit I have difficulties with these texts. In a way, maybe I'm mentally lazy to follow other people's calculations, but it's very cumbersome for me to do that unless I have my own picture in my mind how things might go, or how I can visualize that. So, but you did a great job on yeah, explaining the essential points, and certainly Reisner. I mean, he could have done better in some respect. I for instance, I mean, he has this formula, and if you just compare the physical units, which I always do to get a rough idea what's going on, and so you realize that these MA, MJ are not kilograms. They cannot be kilograms. They have to be something very strange, like square root of kilograms times meter, in order to get it to get it. So what does that mean? I mean, how we could be but
I mean, he calls them just like a constant associated with a mass point.
yeah,
But
that's
the
true.
idea
But
there was that,
concretely, it's. I think it's something. It's useful to think about the units, and it's also. I mean, it widens a little bit your mind to think about also in that manner. To, I mean, at the very end, what you need is also an imagination of the concept. I mean, you can't be a physicist without having an intuitive idea what is momentum, what is angular momentum, what is an energy, and what is mass. But if we want to revolutionize this gravitational physics, which must be done somehow, I mean, I think we have to go also on this level of maybe creating a new concept, or questioning these established yeah, maybe the concept of mass, maybe the units even, and make sense out of all this. I mean, I still haven't made, but it's very inspiring, and yeah, you did a great job in in, I don't know, I mean, making it more accessible somehow, what he did, what Reisner did. I really find it interesting, and yeah,
I mean, that's what I'm trying to do, and partly because I mean it's a headache for me as well to read these papers. You know, it's
glad to see you. But evidently you're more, I don't know, maybe
well,
just younger and more force, more motivation to
I
go
think
through
I
it.
just I mean partly is I mean it's because I'm doing this PhD thesis, and it's kind of like it's what I have to do at this point because I've put myself in this situation, and so I kind of don't really have a choice. But
You're not
so
supposed to be lazy. Yeah.
but it's really satisfying when you read these complicated things, and partly I mean what I'm trying to do in a way is make it simpler so that I can understand it, right? And then hopefully by then explaining it in words that I can understand, it becomes much more accessible for everyone else as well. So that's what I've tried to do with my papers in general. But yeah, I mean with Rice.
If I may, if I may ask you, 7. I displayed the formula 7 here, and it's also, for me it looked already complicated, so I didn't like to go into that. But then, I mean, it's we have the gravitation attraction, and then this, okay, 1/3, then MJ, and then he has in the numerator he has this k squared omega squared, which is well, this should be the speed of light squared at the very end, if you look at this coincidence. So, but now going to the history. I mean, 1915, we had no cosmology, no idea about the true size of the universe, all this. So he couldn't in a way think about that. Or do you think that he had an idea that this could be related to the speed of light, or even in the order of magnitude? Because if at the knowledge, if you with the knowledge of the time, if you put in the speed of light, it doesn't make sense because the universe was much smaller. So I don't know if he was aware of that possibility, because nowadays we see the coincidence we mentioned before. But do you think he had an idea that this could be related, or
I
these?
mean, I'm really not sure because, well, uh, he doesn't mention anything in his
Mhm,
paper. Reissner was an engineer by
mhm.
his profession, so I don't know how much he was in touch with all of the stuff that was going on in theoretical physics at the time. I mean, I know he must have been to quite a large degree, but I mean, 10 years later, Schrödinger comes up
Yeah. Mhm.
with the formula uh, in a much more modern form. You know, G.
Yeah, he explicitly said the gravitational potential of the entire universe could be just c squared. Yeah,
It's c
that's all.
squared or 2c squared or half
Yeah,
squared.
yeah. Mhm.
Yeah,
Wonderful, wonderful paper. But you're well, okay. But to be fair, I mean,
but that's also
it.
before. I think it's the year after or the
Yeah,
year
Hubble
before.
was in 1923 October,
Mhm.
where he discovered he demonstrated that Andromeda is a galaxy. And
Right.
so even if he hadn't discovered the redshift distance relation, and he had not measured yet the size of the universe, the idea that out there beyond our galaxy could be much more stuff, I mean, that certainly has inspired Schrödinger to, because if you just count our galaxy, you get something like 10 to the minus 6. Okay, so you're far off from that, from the true coincidence. But Schrödinger also had I mean, he was also very farsighted in that, I think. Yeah.
Yeah, yeah, yeah. So okay, where were we at now? Yeah.
No, well, okay. You mentioned also that if we show again the Formula 6, and if we realize that in Reissner's Lagrangian, everything depends on that r dot squared. So everything is in relative motion. So you wouldn't have static gravity at this point, right? So this is
So if we're looking at Formula 6,
the of your
yeah,
paper,
yeah, of my
Reissner.
paper, yeah.
Yeah.
So after the two postulates, because I've just got the
Hmm.
paper.
Yeah. I mean, if you just consider or maybe you should phrase it less technically, but for the audience here. But if everything depends just on motion, on velocity,
Mhm.
okay, and you can easily imagine a world without any motion. Okay, it's not real, but just imagine for the purpose of explaining gravity, you don't want to resort to that hypothesis that something has to move. But in this case, you need this motion, this microscopic motion, because if everything stands still, there is no gravity, right? The Lagrangian would be just zero,
Right, exactly.
nothing.
So that's the thing yeah. So in his previous theory from the year before that I also go through in the paper very briefly, um, he has these two different potentials. So he has this potential which is essentially
Hmm.
a relativized kinetic energy term, which is responsible for inertia, and then he has this potential which is the gravitational potential, and a combination of the two give you inertia and gravity. And but then what he suggests in his second paper is, well, actually, if I write the kinetic energy term, so the relative inertia term, in a slightly different way, then I can make it look a bit more like the gravitational potential. But as you say, there's no static field, right? So it shouldn't give rise to an acceleration. And then what he suggests is, yeah, well, what if those particles are vibrating, right? Um, and the way to kind of like explain visually how this works, because it's difficult to see why this would give rise to gravity just from um, just from uh, how to say, like, looking at the Lagrangian, right?
Hmm.
Uh, so in an acceleration relative theory, you have to imagine that if I'm a particle here and there's all of these other particles in the universe, and all of the other particles accelerate in that direction. They
Mm-hmm.
should induce an acceleration on me that's the
Mm-hmm.
same.
Mm-hmm.
So, which means that each of them has to induce a small amount of acceleration. Each of
Yeah.
them has to give a contribution to
Mm-hmm.
my overall acceleration, which means that if
Yeah.
there's a nearby particle that's accelerating, regardless of what the other particles are doing, I'm going to feel a very small acceleration.
Yeah.
Um,
That's the other formula I think Cook has then taken
yeah,
on.
yeah, yeah.
The you call it the Reissner-Schama force, right?
Oh, the Einstein, Wes Cook calls it the Einstein-Schama force.
Right, right.
He gets it from a book by Dennis Sciama,
Yeah,
who
yeah,
is
yeah. I
praising
display this
Einstein.
formula also. That's also very, very intriguing. Yeah, yeah.
Yeah. So then, yeah. But this visually helps to understand what's going on a bit better. And so if I imagine this particle is not stationary, but it's vibrating, and it goes like this, right? It goes from side to side. When it's over here, and there's a 1/r dependence for the inertial potential, right? So when it's over here, it's inducing an acceleration in this direction, and when it's over here, sorry, in the other direction, because it's accelerating this way, so it's inducing an acceleration in this direction, and when it's further away, it's inducing an acceleration in this direction because it's accelerating that way as it vibrates. But because it's slightly closer when it's over here than when it's over here, the net acceleration as it waddles back and forth, the net acceleration on this particle is going to end up producing an attractive force, right? So there's going to be, just because this is vibrating, there's going to end up being an attractive force on the other particle.
You explained it very well. That's great. I really understood it better right now with your explanation.
Yeah, thanks. Because I've been trying to, I mean, myself, and just like looking at this maths and trying to see how it works.
Yeah.
Eventually, after looking at Cook's model in detail, I saw that this is, visually much easier to get.
Mhm.
So yeah, so that's what's going on really in Reissner's Lagrangian is he has this relative acceleration theory, but with the added postulate that every particle is vibrating at some speed. There is like this gravitational attraction, and he doesn't suggest that it's vibrating at the speed of light, but this is something that's hinted at or that's proposed for the first time, as far as I know, in Julian Barbour's model from 1975.
Mm-hmm.
So Julian Barbour basically rediscovers Reissner's theory. I mean, he gives a slightly different Lagrangian, but it's essentially exactly the same theory. And
Mm-hmm.
and he
You're by the way in contact with Julian Barbour. He's also a very interesting
yeah.
figure. I met him once in 2008, and yeah, it was a very interesting conversation. He knew a lot of things, but somehow, I mean, I was maybe too focused on seeing the connection with variable speed of light, which kind of I think he disliked, at least at the time. I don't know, but on the other hand, I had read his book about the end of time, but I hadn't realized he has done such interesting stuff also.
Yeah, well,
So
Julian is very creative, and so it's sort of full of interesting ideas, sort of going all over the place sometimes. But yeah, and he's not very well known for this paper. This is from some of his earliest work, and so this paper has very few citations. It's before his work with Bruno Bottati, where he gets more recognition. Um, but yeah, I think I mean, in terms of ideas, it's extremely interesting what he's proposing. And so he says, he proposes, so unlike in Reissner's theory where the rotation or vibration of elementary particles was just at some angular velocity and so on, at these small radiuses, Julian proposes, well, what if it's the speed of light? And then this would link with these coincidences that were being talked about at the time. I mean, this was the 70s, so these things were fairly well known about, even sometime before then. I mean, that link to Dirac's large number hypothesis and other coincidences like this, right? So So yeah, so that was in 1974, but he doesn't explicitly construct a model with like a vibration at the speed of light.
Mhm.
However, in 1975, sorry, that was in 1975. In 1976, so the following year, and this is another funny coincidence, in the same physics journal, this Italian journal, Nuovo Cemento,
Know what you mean, though, yeah. Mhm.
there was like where everybody would publish at the time. Uh, so this
With Cook's
guy,
paper, right?
yeah. So
Mhm.
this guy, Richard Cook, who's working at like an Air Force academy in
We
the
should leave
United
fundamental physics to these aircraft engineers. What do you think?
States. Right. Yeah, so Cook um, uh, has the same idea as Julian and
Mhm.
Reissner, uh, but in a slightly different framework. So he's working from. So I don't think he had read Sharma's 1953 paper. He just
Mhm.
bought Sharma's book from a few years later, I think,
I see.
Physical Foundations of General Relativity. And in that book, Sharma talks about the physical principles underlying Einstein's investigations and so on. And so he
Mhm.
talks about Mach's principle and the
Mhm.
equivalence principle. And
Mhm.
he gives this heuristic argument that's essentially based on his own vector potential model, but he doesn't talk about the gravitational potential. He just gives the three vector potential that's producing this relative acceleration business. And so from Sharma's three vector potential relative acceleration theory, Cook then derives the gravitational potential uh, in with the same mechanism as Reissner and Barbour. So to
Mhm.
do with this vibration of these elementary particles.
Mhm.
And I mean, when I initially read Reissner's paper, back in, I think it would have been a bit over a year ago that I read it properly. Um, I was, I was struck that Reissner had phrased things in the same way as me, right? Of explaining gravity from the relativity of inertia. So I just decided, I'm not going to call this my idea. I'm going to call it Reissner's hypothesis, and so on. And but I really didn't understand or particularly like his particular idea about the vibration of the elementary particles. But it has grown on me quite a bit, this idea that the gravity might be linked to this
Mhm.
vibration. Uh,
Mhm. Mhm.
and in Cook's model, he appeals to the quantum Zitterbewegung of elementary particles. I think that translates to trembling motion.
Yeah, Zittern is like, oh, it kind of sounds a little bit sick, you know. You if you're very old and you're
Oh yeah, okay.
so zittrig, yeah. Yeah, two sidelines here before we,
Yeah,
maybe. I mean, one thing is, as you said before, if so many smart people have independently, I mean, come up with very similar ideas, doesn't that show something, or at least, I mean, makes it very intriguing. This is one thing. And the other thing, I mean, we live in wonderful times because these guys really had difficulties to find the relevant stuff. Because if it's in another library, in another journal, you hadn't, I mean, either you are working in the library or you didn't have the chance to find all this stuff. That's sometimes it's tragic. I think it's that Dirac didn't read Einstein's thoughts about variable speed of light, and Dicke didn't read Dirac, and so on and so forth. We have dozens of these examples where people just couldn't, were not able to connect the dots as we now have the possibility with the keyword searches and the internet. And
right,
so
exactly. Yeah.
that makes the entire thing even more interesting, I think.
Yeah, and so I think that's really, you know, why the kind of thing I'm trying to do now is it's really the right time to do this because we have the internet and there's so much information being put together, and now with AI as well, you can like search things super fast. I mean AI using AI as a search engine is a bit it can work.
You know
Maybe
what happened to me? recently, I made a video about that. Recently, I mean, Elon Musk made ask Grok a question about gravity. He believed that that was about the fundamentals of gravity, but unfortunately, well, all the modern fashions he didn't phrase in a stupid way a little bit, but no blame to him. But anyway, if you ask Grok in a slightly different manner, and I didn't mention, I didn't suggest Sciama, and I what did I say? Yeah, I was just mentioning fundamentals of gravity, and he came up with Sciama, you know.
Right.
So that's something. I mean, even our generation with the internet couldn't do, right? So I'm convinced these
You have to
models really
be,
understand
yeah.
something, and yeah, they might be helpful. Yeah.
You have to be careful to, to what extent they're being trained on things that are going around. And so if you have some idea going around, it will be reflected in that.
I mean, you could certainly debate to what extent this is real intelligence or whatever, but let's say at least it's another fantastic tool. You know?
I mean, there's another aspect where, I mean, the AI can sometimes be too keen on pleasing.
I know. Yeah.
So
Mhm.
you have to then be extra critical of yourself because it will try to convince you that what you're doing is is exactly
Yeah.
right and so on.
Yeah. That's my prompt.
It-
Contradict as much as you can based on evidence.
right. Yeah.
Yeah.
That's a good one actually. Yeah.
Yeah.
So okay, where were we?
Yeah, I mean, we have touched the theories of Reissner and Cook and also, but then you have, at least if you want to continue that road, I mean, you have to think about elementary particles. What is, I mean, if you postulate Zitterbewegung, if you postulate that motion, which is necessary for gravity, then you have not only all the problems of gravity and cosmology and inertia, but you have to also go to and resolve particle physics, let's say, at the same time, because certainly you would need a model of elementary particles that do the thing you need in this context, right? So we are facing, of course, even a harder nut to crack here. Yeah.
I mean, I think to some degree this sort of reflects what people in the rest of uh, research in fundamental physics and gravity and so on are talking about. And, the dilemma that Einstein was at all the way back in 1915, which is in between giving like a field theory uh, account of gravitation, which is what Sciama's theory also is, um, and like a microphysical explanation of what's going on at a more fundamental level. And I think this is kind of where this is at, right? So on one hand, I'm tempted in my thesis to just stop at Dennis Sciama's model and I'm trying to write this relativistic extension of this model and to make it work properly as a coherent theory. But then there's the challenge of getting the chronometrical effects of gravitation in there as well, and so on. So there's some challenges there. But that would only reproduce a sort of Machian version of general relativity, right? Uh, but if we want to go beyond that and understand, what's, why do, rather than appealing to like a metric or a field or something like this, understand exactly why elementary particles are subject to these modifications in the presence of other masses and so on.
Mm-hmm.
We have to bring in, quantum mechanics and
Mm-hmm.
like a sophisticated understanding of,
Mm-hmm.
the microphysical constituents of matter and so on.
Yeah.
Uh,
I would mention here another coincidence. Not sure if you agree totally, but I mean, another remarkable coincidence is that the Planck's constant is at the same order of magnitude as c, the speed of light, radius of the proton, mass of the proton. If you multiply by a factor of pi over 2, you have very close coincidence. And this is very closely related to Dirac's first hypothesis, large number hypothesis. I would say it's a more intuitive and simpler formulation of Dirac's first hypothesis. And yeah, I think this is something left to explain. But you know, Dirac's large number hypothesis, let's say it's outside mainstream physics. So certainly, if you
Yeah,
want
I mean,
to follow that road of understanding something microscopically about maybe the foundations of gravity also, it's another big task to solve.
I mean, this comes back a bit to what we were talking about earlier, to explaining natural constants, and so Dirac's large number hypothesis was like a respectable, uh, research program for quite a while in the 20th century. So not with everyone, but there was quite a lot of very respectable physicists who were interested in these ideas, and then it kind of went out of fashion. I would say around like the 70s and 80s, uh, started to go out of fashion.
When maybe the cosmological model, the dominant one, was established, because I mean, Dirac's second hypothesis would shred to pieces conventional cosmology, right? I mean, the 10 to the 80 coincidence, the number of particles in the universe being the square of the distance. Why the hell should be, let's phrase it that way, you can cover the surface of the universe with all the protons in the universe. So you have this strange two-dimensionality. The universe would be three-dimensional. You have a density. It's filled with particles, but all these particles fit on the surface. Why? Okay.
Yeah, I mean, I'm not super familiar with all of these coincidences, but yeah, I I mean, I think it's very much, yeah, like an interesting research program, but I'm also interested in why why these ideas went out of fashion, why it became less popular. I think a big part of this was um, the technology producing much more complex and sophisticated empirical data. And so
Mhm.
for example, prior to the 1970s, there was a lot of speculation about, prior to the 1960s, 70s,
Mhm.
there was a lot of speculation about different cosmological models and different
Mhm.
ways, of reconceiving things that often would go outside of general relativity and
Mhm.
into alternative kind of related theories and so on.
Mhm. I
Um,
can, by the way, I can give you another reason, I think, why it went out of fashion, because I mean, Dirac somehow explicitly predicted the change of the gravitational constant. And he was a little bit too confident about that, because if you go into that business of changing constant, I mean, all constants have to change. And it's far from self-evident that in this picture of changing constants, what do you observe at the very end? So this is a very
right, yeah.
difficult question to solve. So people somehow superficially tried to test that prediction and came up. It has become kind of a fashion to come up with all sorts of tests of dot g over g, and I mean. Yeah, some really fancy stuff I don't believe at all, let's say, but there is something which, to be honest, at least doesn't support that change, such as the Viking data on Mars, and that was in the 70s, I think. So maybe there were the first challenges of Dirac's idea from an observational point of view around that time. Yeah, but I don't think it's ruled out, by the way. I don't think so.
Yeah, no, I mean, not at all. I think, I think, but but I think there was also a change in attitude because of the, in the physics community in general, a change towards like saying, oh well, experiment will decide. Um, and I think they kind of threw out the baby with the bathwater to some extent, because there's a difference between holding on to a very particular cosmological model or something and saying, well, this one has to be correct. And therefore I'm going to ignore data. There's a difference between that and having a broader view of there must be some kind of explanation for things, right? And I think what happened is once everybody starts getting humbled by big data science and saying things that were not predicted by your cosmological
Fantastic pictures and telescopes, yes.
exactly. Once everybody starts getting humbled, they sort of retreat and they don't propose any too bold ideas anymore. Um, and there's a kind of attitude of we no longer care about actually explaining, these constants or whatever it might be, explaining the facts of nature from a more fundamental perspective. Because before that, in the 40s and 50s, and before then, I think there was a lot of speculation among like the most respectable scientists.
Mm-hmm. Yeah. Of course, I totally agree here with you. I mean, I might add Thomas Kuhn. You have this growth of parameters, of free parameters. It's a very general methodological perspective. If you look at modern physics, we have lots of parameters, or you call it constants of nature. But I mean, you ought to explain these numbers. Physics is not just juggling around with all this stuff and every couple of years inventing a new parameter. Then we have dark energy, and then we have change of dark energy. So this is this is the wrong method, or it's not enough. There's not enough reflection about these methodological facts, which have been pointed out by Thomas Kuhn. And I think it's even earlier. You can trace that attitude to, I think, 1930, and then you get the rest of the history involved with World War II in Nazi Germany and the atomic bomb, and all that contributed to this huge shift of how physics is performed. Yeah, away from the fundamental questions to the technically describing the data with parameters.
Right. Yeah. Yeah. I mean, you've written a book recently. I haven't read it yet.
Yeah, that's the Make Physics Great Again. Yeah. It's also, I mean, it's also history, but a little bit in another kind. I mean, not history of science in the strict sense, but also taking a more general view. What's the evolution of ideas? How? Yeah, and we have this. I mean, we have this tectonic shift that in the middle of the 20th century. That's, I mean, the power, be it military, political power, shifted from Europe to America, and also the dominant scientists were in the United States, and how science was done. Einstein lived there, but if you look at his what he did in Princeton and how he was respected, or not respected, tells you a lot about how this attitude has changed. Yeah.
Yeah. So supposedly the Americans are meant to be pragmatists, philosophically inclined, or something like this.
Yeah. Well, there's a lot to say, but this is your interview today. So, what do you think? What do you plan? What do you think is promising? What do you dream of, and how to continue that? Do you have hope, or what?
Well, I mean, so what I want to do with my thesis is really like articulate these hypotheses properly, and get out of some of the controversies of whether is Mach's principle even a philosophically valid idea or not, and so on, and just formulate things in terms of hypotheses which are either true or false of the world, right? And say, look, if this is true, this is very interesting, and we should look into this more. And hopefully that can help at the very least, to try to put this research program back on its feet, and give it some legitimacy. That's what I'm hoping for. And then, I mean, my broader project is to decipher the things themselves, right? And, I mean, I've proposed this thing that I've called Reissner's hypothesis, which is to explain gravity in terms of the relativization of inertia. I also have some hopes that you could make an analogous argument concerning the chronometrical effects of gravity, or the metrical effects of gravity. So, for example, how gravity modifies the size of objects in a very subtle way, but it modifies the scale of objects. And I think you can make an argument analogous to Mach's principle that under scale transformations of the universe, you should have the relations between things stay the same, and therefore the physics ought to be invariant.
There's also Julian Barbour has published a lot about that idea.
Exactly.
Dilatational momentum and this, yeah.
Exactly. Yeah. And I wanted to sort of do a little thought experiment of like, well, this wasn't really spoken about in the late 19th century, but it could well have been, right? So it could well have been that somebody said, and Einstein makes remarks kind of along these lines retrospectively in the 1920s, but somebody could well have said, for example, well, not only when a body is not subject to forces does it continue to move in a straight line, but it also stays the same size, right? If it's a rigid body, it at least approximately stays the same size and shape as it moves, right? With respect to other bodies. And now, is this size determined by its relation to absolute space? So, right, is there some absolute metric that's determining the size of that body, or are its metrical properties somehow determined by its relations to other bodies? And so I think using an argument along these lines and then imposing invariance on the scale transformations, it might be possible also to argue somehow for the chronometrical effects of gravitation in a Machian way, rather than in the way that Einstein wound up doing by varying things locally, his general covariance principle and so on. So yeah.
Can we find something we disagree on?
I mean, maybe some subtleties, but like
yeah. Well, you mentioned that Dirac's hypothesis is interesting. Maybe it's not a really integral part of what you hope to include in your thoughts, or just it's on hold a little bit. Where if it comes out, it's nice, or do you think it's something really essential that has to be solved?
I mean, to me, it's not clear exactly what the precise idea with Dirac's proposal was, and it's I mean, what it suggests is there's a connection between G, between the size of the atom and the size of the cosmos.
Well, I think you can fairly phrase that fairly precisely. Actually, you have 3 numbers and you have 2 equations. That's, I would say. And the first number is the relation of the electric and the gravitational force, 10 to the 39. Then you have the size of the universe of the size of the proton, 10 to the 40. And the first hypothesis is these numbers are equal or related. And then you have the third number, the number of particles in the universe. It's 10 to the 80. And the second equation would be, or second hypothesis would be, this is the square of the first number. So it has certainly explanatory power. I mean, of course, you can doubt whether the entire.
Well, it's a coincidence, right?
Yeah, it's a coincidence, but I mean, the revolution would be, of course, provide that explanatory power, make a very nice convincing theory around that comes up, that justifies this.
Exactly.
Yeah.
And so what I would see is well, if we have I mean, the hypothesis is like a hypothesis in the sense that there's a hypothesis that there's a theory that would explain this, but the particular theory hasn't been articulated. And I mean, certainly there's
Right.
some.
It's
We have a
less
variable,
even much less developed than things like Sciama and or Reissner. I agree. Yeah.
right?
So it's really less concrete in that sense. I admit. Yeah. Yeah.
But in general, if if you have a variable G theory where the gravitational constant is getting weaker over the epoch, then that makes kind of sense, along these lines, right? You would expect the epoch to be associated with the weakness of the gravitational force and so on.
Yeah, but I mean the change of the gravitational force. I mean, if you believe in Sciama's hypothesis on the gravitational constant, then you are almost there already. I mean, because what is the horizon? I mean, the horizon is something that changes. The mass which is visible inside the horizon is changing. So G or even C should be changing as well, right? There's almost no way to escape from that.
Right. Yeah.
Yeah. What do you think about Robert Dicke? I think he is also a very, for me, he's also a genius with his idea that matter in the universe could be at rest, more or less. That's, by the way, I mean, we can implement this in the theories of all these relational theories. I think it's a good idea to do that in the way Dicke has proposed, but yeah, I haven't seen an enthusiasm so far. I mean, no blame at all. Just, I mean, you have.
What do you mean that matter could be at rest?
Hmm?
What do you mean by that? The matter could be at
Yeah,
rest?
I mean, Dicke says that the Hubble redshift could be basically an illusion, and it's not just the
Oh,
tired
right. I
light.
see.
It's
Yeah,
not
yeah.
just warming up the tired light hypothesis, which you could say, okay, you need to postulate extra things for the. No, he provides an explanation. He has explanatory power that necessarily you see that redshift because C is changing and you have certain laws governing the where the change of the gravity of the speed of light goes. It has to go into the frequency where the light wavelength has to be conserved during that propagation in the universe, and that necessarily would lead to a redshift. So it's, in my
I
view,
remember
it's
you
very
pointed.
simple and very explanatory for the Hubble redshift. So that's why I am fascinated personally, and I try to link it to Sciama and Schrödinger and these guys.
I definitely think that yeah, if that turns out, if that works out, that would be a much more elegant solution than but there's also a point about the versus redshift versus expansion of the universe that I view this as kind of conventional, uh, that there's no matter of fact as to which one is actually happening, right? Because you can say that everything stays the same size and everything's moving away from everything else, but that's exactly the same thing as if you suppose everything stays where it is, but it just gets smaller, right? Um,
Right, but you have to provide a mechanism for the redshift, which I'm not sure these Barbour-like ideas can do.
um, I mean, yeah, I mean, you need a mechanism, you need an explanation. I, you know, but I, I mean, what I wanted to say is basically that I also favor your way of thinking about this, of thinking of things are getting smaller in space rather than space is expanding and
Mhm.
distance between things is increasing.
Mhm.
Because, I mean, I wrote this whole paper uh, about the concept of space. I think there's been a lot of confusion about, yeah, this concept space since since the advent of non-Euclidean geometries, essentially, because we formerly had this notion of space not simply as like this thing that we're embedded in, which moves around and stuff, but rather as like a conceptual construct that's simply used in order to coordinate how things move with respect to one another, right?
Mm-hmm. Mm-hmm.
And that kind of space, which is kind of associated with the Neo-Kantian tradition, is viewed as totally passive. It doesn't act on things. It's simply what you presuppose in order to imagine things acting on each other, in order to picture things acting on
Mm-hmm.
each other. And if you take this concept of space, the expansion of space makes absolutely no sense
Mm-hmm.
conceptually. Like that doesn't mean anything.
Mm-hmm.
So the expansion of space is a different concept of space that people have in mind, which is this physical space. The issue I have with this is that if you're conceiving of space as a physical thing, well, it's like other material things. Like it has properties, it moves, it has a
Yeah.
particular size, and so on.
Mm-hmm.
And so you're implicitly kind of imagining a conceptual space within which that physical space can move and have all these
Yeah.
properties, right?
Yeah. Yeah.
And
I
so,
might be misunderstanding you, and there is a risk of talking. We were talking past each other, but maybe not. My take on that, I have also some reservation here with these modern concepts because they're telling you no, the galaxies are not receding as Hubble believed, but space itself is expanding, and there is indeed observational evidence against that naive receding of galaxies, right? Because I think it's the Tolman brightness, surface brightness, or something like that. Pretty much evidence against that. And to me, that additional postulate, which all the modern relativists come up with, oh, space itself is expanding, it's just introducing another ad hoc assumption in the back door that fixes a problem but complicates things. I think that's another complication of this, and all what follows, that you have this horizon and that and then the material horizon, and then this horizon. This is a complication just to account for anomalies. So
that may well be the case. I mean, I'm not
yeah.
so familiar with all of the details here. So
Yeah, there are lots of it's a separate still a separate history of modern cosmology and all the anomalies and all the data. It's a little bit another issue, yeah. Yeah.
yeah, yeah.
Okay. Anything else on your list or on my list? I
No.
think, yeah. Yeah, what do you respond to people um are you doing this kind of stuff before Einstein? But we have wonderful working cosmology. Don't you know that we have evidence for reionization? Don't you know we have all these beautiful gravitational waves? Don't you know that we have pulsars that, I don't know, verify, prove the second or third post-Newtonian approximation of? So there is no room. The space of alternative theories is closed. How would you respond to that?
So I mean, my whole approach is really to look at the foundations of theories, not to look at all of the details of all
Mm,
of the experimental results that have been coming out. But
mm,
I mean, my view is that there were serious philosophical problems with how uh, general relativity was arrived at, and the foundational ideas underlying it uh, that were never resolved, and that the intentions with this theory were not fully achieved. And so I'm going back to those things and looking at, well, if we try to if we try to do this again, from the principles, where else could it take us? And then my view is, and it's the same as Einstein's view, essentially, that you should start from the principles, arguments, and if you've hit something that's true, then it will give you so much more late down the line, right? So if you've realized something true and profound about nature, you're going to find it solves all sorts of problems down the line, and you don't need to busy yourself with all of the details and get lost in all of those things
Mhm.
to do that kind of investigation.
Yeah.
And of course, not everyone should do this, but my appeal is like at least maybe some people should give this a try, and it's not a huge waste of resources if my particular attempt doesn't succeed or whatever. Um,
Mhm.
there's plenty of money being wasted in much more grandiose ways, right? So,
Mhm.
yeah.
That's exactly what I think. Thank you for your firm stand. And yeah, maybe we can conclude, since you're also philosopher of science. I like the Wittgenstein quote, always take, how does he say? Always go to a place where there is a overview, even if this view is not yet clear. Yeah,
Yeah, exactly.
that's the right approach. Okay, thank you very much, Jonathan. I hope we will further collaborate. I'm curious to see your work, following your work, and thanks again. Very personal that you reignited my interest, and you told me some lessons. I should sometimes look closer and not be mentally lazy in reading old stuff. That's really great the way you work, and I really appreciate this. Thank you very much.
Thanks so much for your support. Yeah, I'm
Okay.
really glad that people are finding value in what I'm doing. So, yeah, cheers.
Okay. Thank you.